Good afternoon, everybody, and welcome to the webinar. This is the simulation motion webinar. It's talking about time and event-based simulation motion. My name is Asfand Kuki, and I'm Technical Simulation Product Manager at IntercadDirect. And let's start with our presentation. All right, the objective of this presentation is to demonstrate time-based and event-based capabilities of SOLIDWORKS Motion to understand the dynamic performance of your design. What we do at the first section of our presentation is going over the definition of rigid body motion and basic laws governing. Have a definition of kinematic and dynamic system, explaining what is degrees of freedom and how we can restrict this. And also we will go through the contact advanced settings and calculation options. In the second part of our webinar, we will have a case study for a time-based motion. We'll be analyzing a Catapult assembly. We'll be checking the performance of the assembly, as you can see in the picture, as well as we getting the required force to operate such a motion. In a pre-processing stage, we will review the CAD geometry and assembly mates. We will learn how we can create a time-based motion study, how we can apply loads, friction, contact, spring, and gravity. And also we will review the contact advanced setting and how we adjust the calculation option to get the answer. In the post-processing stage, we will create a review and the required force as a 2D plots, as well as we do some animation on the performance of the actual assembly. And the last part of this presentation webinar is to go to the event-based case study, where we have a feeder sorting system assembly with a couple of actuators, as you can see, where it's trying to push different boxes into the different bay. So basically we will review the let's say CAD assembly and mates, and also we'll learn how we can create an event-based motion. We applying servo motors, proximity sensors and contacts, and also we will introduce the difference between event-based and time-based. Well, basically we're creating task here, we're getting the triggers of the task and what sort of action coming from these triggers. In the post-processing stage, we're definitely going to check the performances of the assembly by an animation. All right, so with that overview of what we're trying to do, let's start with the first part, which is definition of mechanism and motion simulation. Basically, a mechanism is a mechanical device that has the purpose of transferring motion and or force from a source to an output. This is what you design and what you desire. Study of such a moving system is what we call motion analysis. So the base assumption in a motion analysis is to understand that all the parts are rigid, they're acting against each other, and they can react at the same time. What is important to determine in a motion analysis are how the parts are interacting. Well, we call it as mates. The mass and inertia properties of the components, as well as forces, motors, and actuators, and obviously the time factor. So how fast or how slow and when all of these forces are acting. One important note before we really go into the case studies is to understand the mechanism types. We have two types. One is the kinematic system and the other dynamic. As you can see in this first figure, we have a lifter system, a jack which is pushing the lifter and it's traveling from point A to point B. Regardless of the mass, how big or how small the lifter is, the whole, let's say, assembly has one task to do, moving from point A to point B. Therefore, we can simply say there is one solution to such a system, moving from point A to point B. Therefore, we have 0 degrees of freedom, and the movement of the components are simply being enforced and constrained. One solution just from point A to point B. So this is regardless of how big, how small, and what sort of forces we are applying. This is the ultimate goal. However, if you look at the series of spheres hanging from the frame, depends on how big are the spheres, means the mass, or how much you're lifting the first sphere, the solution could be variable. Means bigger spheres, more impact, maybe different results. More lifting height is simply back to a different result as well. Therefore, we have more than 0 degrees of freedom. And also, the forces are partially controlled, and infinite number of results, depending on the force, are available. So it's very important when you're setting up a motion analysis to either have a kinematic system, means 0 degrees of freedom and one solution, or either you go for a dynamic system where you might have multiple solutions. What we have to avoid for sure is to over-constrain our system. Basically, the mates or the forces or the gravity or anything else you applying to the system are simply conflicting and canceling or, let's say, acting against each other. That is the first note, and it is more than important. However, this specific topic is quite advanced, and we can have a more discussion in upcoming webinars or in our training. All right. Now, let's look at the basic laws. Newton's first law is what we have, and everybody knows. Everybody preserves in its state of being at rest or moving uniformly straight ahead, except insofar as it is compelled to change its state by forces impressed. Basically, it says any object will remain on the situation that it is unless we applying force. Second law is conservation of momentum. It is simply stating that sum of externally applied forces on the body, sigma F, is equal to the rate of change of linear momentum P. So dP over dt means rate of change over the time. T denotes time, P denotes momentum. But in a very simplified version, we all learned that if we have a constant mass, sigma F equals to ma. And the third law is about sum of the moments about the center of mass of a rigid body, sigma m, due to external forces, and couples should equal the rate of change of angular momentum h of the body, dh over the time. So these are the three basic laws. Those equations are getting solved when you set up a motion analysis, and the answer will be provided. Okay, with that explanation, let's go to a very important note. What are the differences between rigid bodies, rigid and flexible assemblies? As we said, it is more than important to understand in a motion analysis or rigid dynamic analysis, all components are infinitely rigid without internal deflection within a part. So there is no contact deformation or deflection on the parts. What is happening is simply parts are acting and transferring load from one to the second. No deformation or change shape during the motion. Those rigid bodies could be a single part or an assembly. Now, the second note I would like to put here sorry, is that you can set your assembly to be fixed or make it as a state of rigid. A rigid assembly will have the same concept of all the components are rigid without internal deflection. However, as we have multiple bodies within a rigid assembly, simply they are attached together or welded and they are acting as a part. While the flexible assembly has the same concept of all components, individual components, are rigid without deflection, but they can be moved or interact independently. So do not forget, in a motion analysis or rigid body dynamic, we have no deflection and no change of the shape during the motion for every state of part or assembly. However, we might have a big assembly that 10 components are simply welded together and acting as a part, or all these components to act individually. That is a very important note here. So do not forget, that is the highlight of what I said. Components are infinitely rigid without internal deflection. Okay, now we're reaching to degrees of freedom. Basically, each body features 6 degrees of freedom. Every object in your space can translate in let's say direction, X, Y, Z, or have 3 rotation degrees of freedom by rotating along the axis X, Y, Z. And any restriction you put, it's either go to restrict X, Y, Z translation, X, Y, Z rotation, or all of them, or some of them. So basically, as what you experience with SolidWorks CAD design, you might have some fixed part. That simply means all degrees of freedom are fixed. And you might have some floating parts that some of these degrees of freedom are unconstrained, or let's say none of them are unconstrained. So as we introduce the degrees of freedom, let's say how we can, let's say, geniusly or to the point, we can restrict the movement of a part relative to another. That's what you learn as a mate connection. There are a couple of, let's say, mates. Well, it's very, let's say, has a lot of variety. The first type could be a concentric mate between 2 solid bodies. Basically, we have 2 circular faces or axes or circular faces that could be concentric, could be a hinge mate, or could use our reference, let's say, points, such as point-to-point coincident mates, or have 2-face coincident mates, or point-to-axis coincident mates. There are more options. Well, you have advanced mechanical mates such as screw mates and lock mates, and also universal mates. But what is the outcome of putting mates is to constraining our degrees of freedom, or enforcing our mechanism to move or act in some certain way as we want it. Again, putting the mates might end up with having a kinematic system or a dynamic system. What we have to avoid is to over-constrain our assembly. Okay. The other way of doing constraining degrees of freedom is to apply either linear forces or motors, either linear or rotary, or activate the gravity. By doing so, as you can see, you are enforcing the components to act or to move in some certain degree or some certain direction. Gravity will enforce your object to fall down in a gravitational field. So either you're putting mates or either you're putting force, motor, or gravity. That's how you're constructing your degrees of freedom. So in order to do the motion analysis, we have a design, we make them, and we applying some force, motors, or gravity. What we have to check is to make sure either we have kinematic or dynamic system. All right. Now, with that introduction, we go to have a quick check about the case study 1, which is a time-based motion. You can see it's a Catapult system, as you can see in the picture. It has its own frame. A system of hand crank will rotate, and within a pulley and belt system will make the arm to rotate and position next to the projectile and projectile holder. Also, there is a trigger mechanism Well, within the movement, we'll bring that holder off and make the projectile move and get loaded to your catapult arm. So as a review, what we will do first in our hand crack, we are going to make a 990 degrees in 3 seconds. Means simply we're putting the catapult arm into the position. And then disabling this motor after 3.7 seconds to make sure that the projectile is loaded. Now, due to the counterweight, the catapult arm is getting released as the motor is getting disabled and the projectile is thrown up. Then what we do next is to have a closer look at the trigger system. There are 2 components in our trigger system. Well, they're coming into the contact, so we're checking their interface at the right time and making a contact between them in order to release that mechanism at the right time. Then we have a definition of contact between these solid bodies. Obviously, the other components has the group contact, such as the let's say projectile holder, all the components with the projectile. We will learn how to do this group contact. And obviously the third type, which is the contact we have with the projectile and the catapult arm, which is a frictional contact. So either we can have frictionless or frictional contact type between 2 bodies or multiple bodies. And the last thing we are doing in our pre-processing stage is to define a spring force with a dampening factor to push this projectile into catapult arm. So this is the pre-processing stage and problem description. What we are expecting to see at the end is basically the motion of our assembly as well as detailed plot of torque required for this rotation, also spring displacement, spring velocity, and spring forces. Alrighty guys, now it's the time to move to actual assembly. Here it is, and you can see a big list of the components, all parts. One is fixed, which is the base. Some of them are floating. Some of them have been restricted. The type of the mates are all here and we can review. You can see variety of mates has been used, such as coincident, concentric, even gear mates, and etc. Now, before we doing anything with the motion analysis, let's examine the assembly and look. What I would like to do is simply turn the handle. You can see when I am turning, the catapult arm is coming down. That is the first thing I have realized. Let's say what is happening to the other side, which is a trigger system. This trigger mechanism got 2 objects, 1 and 2. When coming to a contact, it should push that component, will end up with releasing the holder. That will enable us to move the projectile and load it here, and then releasing the motor force that is going to go back and release the projectile. So that is how it's been made. Right now there is nothing else I can do. The project has been defined very good in the state that it is going to work. Now what we are going to do next is to make a motion analysis by applying contacts, force, gravity, and everything, and make sure our design is working perfect. What is important is to simply do the start of motion analysis creation in the way that we would like the assembly to start from that point. So in order to do that, because there is no rewind for me, I have to reopen my assembly here. Let's reopen it. And this is the status as I was expecting. Now, in order to create any motion, let's say analysis, first of all, you have to activate the motion analysis add-in. With the correct licensing, you go to your add-in, and there is a motion add-in tick. Well, it needs to be ticked on. Well, that is enabling your motion studies to be created. For every assembly or part, there would be an automatic motion study 1 tab created. However, by right-clicking on this, you can create a new motion study, as I'm showing you. Then it's coming to this communication box. You can see there is a motion analysis tree. Well, all parts are being listed, and also the mates are listed here. The first thing I would like to mention here is enabling or disabling mates in a motion analysis will not affect anything in your actual CAD model design. So if I suppress the first concentric mate and I will back to the model mate, you can see it is not been restricted or suppressed. Means in any motion, the mates are automatically getting transferred. However, we can just add mates here in our motion analysis, suppress the existing one, delete them, or anything else as we might desire to do. This simply doesn't mean that it is going to have the same change on your model. That is just a local definition of the mate here. That's the first important note. Now, looking at the menu bar, we can see we can go for animation analysis. Well, there is nothing, let's say, specific you can do here, just as a quick animation file without really calculating any forces or, let's say, the reality of your assembly performance. Basic motion, well, it is restricting some, let's say, function of the motion analysis. The motion analysis is the tab we have to always use to make the correct calculation and get the, let's say, desired output. Looking at the other options, if you like, then this is the calculate option. Always after you do the setup, you click on calculate. You can play from the start your animation, play it, stop it, and have a control about the speed of the animation. You can make an animation save or going over the animation wizard. The tools you have are simply look like you applying motors, spring, dampers, forces, contact, gravity, or post-processing tools such as result and plot you're defining here. You can have a control over your motion study properties at this tab, or at the end, if you are done with your motion study and now you are interested to see the actual let's say deflection within the part, how much stress, how much deformation is happening, you can transfer all the motion forces to individual parts by doing a simulation FEA setup. Okay, guys, now we are ready to go and do our motion analysis setup. As we said, the first thing we have to do is here, make this handle rotated by 2.75 turns, or equal to 990 degrees, acting just for 3 seconds. How we do that? Simply you're going to have a motor. Clicking on this, you will have the option to select a rotary motor or a linear motor. Simply by selecting a component edge, face, or vertices, you can apply a rotary motor here. Well, I'm going to have this circular edge, and it is showing me as automatically being selected for the direction same edge. I can reverse it. Now, this movement is going to define in accordance with the same selection. However, the rotary motor movement could be selected according or relative to another component by simply go and select that component. So a motion, linear motion, could be relative to the same part or relative to the other part. That depends on your selection. Direction can be changed. Then the motion type. You can have a constant speed of a rotary motor with, for example, 100 RPM, or have a distance, oscillating, segments, data points, expressions, or a servo motor. In our case, I'm selecting a distance. Let's say 990 degrees, starting from 0 seconds and at 3 seconds. If you are done, you can see by clicking OK, you will have the first object in your motion analysis tree. Rotary motor 2, and simply starting from 0, the total simulation time is 5. Now, as we said, this motion or that motor should act for 3.4 seconds, and then it should be off. The reason behind that is to let the Catapult system to be loaded within 3.4 seconds, and then we're releasing everything, and due to counterweight, it's going to throw out the projectile. In order to do that, you can see this is acting from 0 to 5. All mates, as I'm showing you in a second, are acting during all the motion time. I can have an adjustment by simply first zoom in to my time frame, select 3.4, right click and say off the motor. The motor is going to be off at 3.4 seconds. Okay guys, now we are ready to have the first calculation and look what we have done. By go to calculate, I'm ready to see the effect of the motor. But before this, I would like to go to motion study properties. Right now, it's a very coarse time frame and recording, like 25 frames per second. I would like to have more frames, means letting the software to have more time to do the calculation, up to 50, and clicking OK. Now, if I'm selecting calculate, that is the motor which is getting applied and position this one here. Let's have a closer look. Zoom in. This time, no need for calculation. I have to say play. You can see the zoom out is automatically been like that. I would like to stop, get it back, right click on the orientation and camera view and disable playback of beauties. That will enable me to zoom in and play without zooming back automatically. So the handle is going to rotate up to 990, up to 3.4 seconds, positioning the catapult arm as the handle motor is simply getting off after this point and there is no other forces. It's simply going to displace further. So what I need is to make sure I'm firmly positioning that arm after that second. Okay, that is the first thing we have done. Now we are ready to move to the next stage where we talk about the trigger system. At the moment, you can see the trigger system is acting by passing through each other, not really detecting the contact. What I have to do is to manually add the contact at this system. But the question is when these two components are coming to a contact. Okay? In order to find that, you can always go to your top level assembly, right click and say, I would like to check interferences. By clicking so and selecting component 1 and component 2 of the trigger mechanism, and find now it's going over the whole motion time and finding the interferences at any time frame which is happening. So the first one is happening at the time frame 132, which is equal to 2.620 here. By clicking on any of these time step, you can see the graphical area is updating and you're getting more and more information about what you have. Details of interferences are simply by volume, area, corner 1 and 2 XYZ, and the length of interfering surfaces. Okay, so with that one, we understood the first time that these two trigger or these two components are coming to a contact happening at 2.620 seconds. In order to find that in our motion analysis, I have to go back, reset everything at 0 seconds, and this is the right time to set my first contact set. As we said, here is the contact, simulate contact between the selected component. Clicking the contact, you will get the option of having two 3D objects as a solid body or two 2D objects as a curve. In the selection box, you might select the first component and second component. You're telling the software there are two 3D objects, component 1 and 2 are in contact. The next stage is to select the material for them. So as you can see, there are a couple of options here for material selection. Acrylic, aluminium dry and greasy, nylon, rubber, dry and greasy, steel, dry and greasy. So if I select steel dry for either of them, simply I will get two more important information from the software. First of all, there are some friction predefined for steel dry. As you can see, the values grayed out, means there would be a testing between two steel dry objects and find out what is the dynamic and static, let's say, friction factor, as well as if these two objects are coming to a contact, how much impact and how much stiffness and how much dampening might be happen, how much penetration it might cause. Therefore, as you can see, it is a very huge information and requires a lot of, let's say, effort to get this information for some specific material. We have some restriction on the typical material here. Otherwise, if you are very specific to your material, you need to have these experiments done by yourself or get it from the literature to make sure when you're defining your contact as the basis assumption of motion analysis, say it is fully rigid, no deformation, but we can adjust our movement by applying some friction and also make some part of this energy to dissipate as the impact or elastic properties. That will make our motion analysis more close to the reality. Considering the fact we are simply saying everything is rigid, perfect occlusion, and when two parts are contacting, they are going to apart and going forever. But this is not reality, what's happening in reality, and we can adjust those by saying the impact or elastic properties and also friction. Okay, so for this contact, as we said, we're assuming steel dry, we're adjusting our, let's say, movement by saying it is no friction happening here, and there are some impact as default. Okay, so if I'm happy with what I've done, I'm clicking OK, and you can see there is one more object happening in our motion study 3, solid body contact, and it is acting all over the simulation time. Next is the contact we have between multiple components, how we can do that. So basically, as you can see, we have a couple of components in projectile holder section. So if I select contact again, solid body, And if I tick on contact group, then projectile is in contact with multiple objects, 1, 2, and 3. So that will save us a time to do the contact definition. Alrighty, so with that one, what I would like to do is to make them as still dry for the material, and there is no friction between them. But again, it is your choice to have it more closer to the reality or just have the estimation. Basically, each contact will add some complexity to your model. Okay, so this is the second contact as a group contact I have defined, and it is appearing here for me. Now, the last contact I would like to define is the contact between the projectile and the arm, which currently they are not in contact, but they are coming into contact later on. This time, I would like to define the friction. Okay, so I'm going to contact solid body as I just have two objects, 1 and 2. This time, I will select the material here on my projectile, and simply this time I'm clearing, the material here. No material I have selected, but instead of selecting the material, the effect of material is to say I would like to have friction. Now I can modify the friction. If you disable the material, the predefined friction values are not here. I can do a modification. The first factor is dynamic friction velocity, and we have the coefficient for dynamic friction. Similarly, you can do the modification for static friction. This is 0.1, and I would like to modify the static coefficient to 0.2. More detail about the friction, what is the difference between static and dynamic, could be explained in an upcoming events. But basically, we're trying to tell the software there is a resistance between the movement of object 1 and object 2. There are some force required to make the movement from static position, and there would be a different force required to maintain the movement. Okay, so I'm happy with what I've done, and this is my third contact. Okay, now we have done our 3 contacts. We have created our rotary motor, and what is remaining, as we might expect, is when this arm is coming to the position by defining the right contact and that holder is being released, there should be a pushing force behind the projectile to make the push and place it on the arm. That is a spring force. By clicking on the spring, we have a new communication box which enabling us to do linear spring detection option or torsional spring. So as we would like to make a linear spring, I'm selecting to locate my spring between phase 1 and phase 2 here. Then after that point is the properties of the spring, as you might need it. First of all, is it a linear spring? Basically, you know the spring force is defined as F equal to K, stiffness of the spring, times X, which is displacement of the spring in the power of N, where N is a component. If N is 1, then you have F equal to Kx, a linear force application. That N could be 1, 2, 3, or 4. So basically from 2 to 4, you will have a nonlinear force. Or it could be minus 1 to minus 4. So the minus and plus is simply defined as positive force repels the 2 parts and negative force attracts the two parts. As we would like, we have a linear spring here, and the stiffness of the spring, as I might like it, it is equal to 0.15, so I'm modifying the value. And also the free length is 13 millimeter. I'm putting this. Now in the next section, you can see there is a damper option. So basically, if you have just a spring, when it's just getting squeezed or stretched, it's going to oscillate forever, in theory. But the reality, as you have a dampening, let's say on each material, you can specify it here and make the energy dissipation calculated. Dampeners are simply have the same sort of exponent from 1 to 4 or minus 1 to 4, so linear dampening, and the dampening, let's say, coefficient is 0.1 Newton per millimeter per second. And the last setting is about the coil diameter, which is 4 millimeter. Number of coils, which is 5, and the coil wire diameter, which is 0.5. Now you can see I have created a spring which is preserving a force back to my projectile, and when this is getting released, it will push the projectile to catapult. Okay, so clicking OK, and still I can see I do have all my objects, all my forces, contacts acting all during the 5 seconds of simulation, except the rotary motor. Okay, now it's a very good time to have a test from what we've done and how the assembly is going to act. All right, I do my calculation here. So start, and it's a very important event happen. The projectile is simply being thrown out to the air. Well, that is not exactly what I would like to do. So you can see there is no release, there is nothing else happening, and just projectile is being thrown out. Should be something that I have forgot, and that factor is basically gravity. So there is no mass calculation here at all when the gravity is not acting. So I have to click here, make sure it is acting on the right direction, which is Y, and clicking OK. Now I have done all my setting here, and it is ready to go for the main calculation. In order to show you the correct things, guys, I would like to not waste your time to do the calculation. It may take some time. That calculation has been done, and you can see it here. Now I'm ready to play the animation, as you can see it here. The animation could be faster or slower. You can see this arm is coming to the position. As long as it's coming, it's releasing. The projectile is going to have the actual position and thrown up. This is the effect of counterweight. So all of this is coming to calculation with the gravity option. Now we are in the point of saying, yes, that looks, the mechanism works all right. Now I would like to make a motor selection. I said this needs to be rotated by 990. Therefore, in order to do that, either it's a person to do that, or it could be a motor to do so. To select the motor, I would like to know about how much torque is required. That simply brings us to the result section. Any plot of the result can be created by clicking here, and you will have the option of selecting a category. That could be a displacement, velocity, acceleration, forces, momentum, energy or power, or other quantity. For example, we selecting forces. Subcategories of the force is motor force, motor torque, reaction force, reaction moment, and etc. Okay, and then you would like to know the magnitude x, y, z component of the force. When and where is simply its rotary motor. By clicking OK, I have created my first plot. It's simply showing us that we need to have this much torque at 3-second maximum. The rest of the torque required is, as you can see, the plot. This will enable us to select our motor at the peak time as we might require. Alright, there are more options we can explore here, as I have created a couple of plots such as displacement velocity, linear displacement, or either linear velocity, or even angular displacement velocity or acceleration as you might like, magnitude, and says I'm showing or selecting the linear spring to look at its linear displacement. By clicking OK and say show plot, I can find this. So a linear displacement is from 6 to 13, means being squeezed and then released to its original length, which was 13. Okay? Similarly, the reaction force has been created, and definitely you can have a look to your reaction forces. And last plot I have provided is the motor torque, as we have created a double here. So it's your option to define any plots by selecting the category, subcategory, and the components of that property. You can have a new plot or adding plot together and have a multiple presentation of the properties. Okay, guys. Now that is concluding our first case study, which was an event-based. So basically what we have learned, you designing a mechanism, and within that design you would like to check the forces, displacement, velocities, and etc., as well as the performance of your assembly. What you need to understand, you have to have a motion analysis to calculate everything, and also you have list of the parts and mates. Well, that could be suppressed or deleted, and it will just affect the motion study. All your options are simply here: motors, spring, forces, dampeners, contact, gravity, and anything else. Simply, they can act on the whole time frame or partially acting and then get disabled. That is true for any of your forces, your let's say contacts, or either could be on your mates here, as all of these components have the option of right clicking and suppressing or place a key or make them off. Okay, now this is a summary of what we've done as event-based function, everything with respect of the time. Now let's move to our second case study. In the second case study, we would like to explore the options for event-based motion. Okay, let's move on. The second case study, as we said, there is a feeder shoulder system. We have 3 actuators and 2 boxes, 2 bays for solid boxes. As you can see, we have 2 types, one without the hole and the other 2 with the hole. What is our aim? Simply, when these boxes are falling down, the correct actuator is pushing it up to the correct bay, and then the other actuator is simply push it inside the bay. So what we're trying to do is to first applying the servo motor to actuator 1, 2, and 3, Then after that point, make sure you have some sensor to understand when the boxes are falling down and reaching to some certain, let's say, location, make the actuator active. Then after that, we have to understand there are some contact between the components, like you have a contact group between the boxes and the pathway, or between all the boxes, and also between the base and the components. Then, when you have done this setup, the major difference between what we get in event-based motion and the let's say time-based is you are creating a task and give it a name. You have a sensor to trigger an action, and then you have an action which simply let's say making a change or making something on or off within a time frame. Okay, as a result, we'll go and review the performance. Okay, let's go back to the model, and this time looking at the feeder sorter. Here it is. This is our assembly. You can see there are 3 actuators. There is a sensor, pathway, and we have the boxes. 2 base, and we would like to do the event-based motion. So creating an event-based motion is nothing, let's say, extra by right-click and create a new study as the motion one. You can always switch between event-based motion and time-based motion. As you can see, I would like to have the time-based or event-based, like this one. Now, the rest of the let's say setup would be fairly the same thing, but with one extra note. As we said, we have to create task. Creating a task is very simple. When you switching to event-based, you're getting an empty table like what you can see. There are some, let's say, tasks being created, but click to add a task will enable you to make a new task. The first thing is to give it a name. Second, if there is a description you would like to add. Now it's saying what needs to be triggered in this task. What is really triggering it? It could be a sensor which is triggering it, or at some certain time it's getting triggered, or if a task or a previous task has been accomplished, it's going to be triggered. Okay? If we would like to make an alert or task end or task start, we can do in a condition. And also, we would like to put any delay, we can put it here. So a task has been triggered. Now what is the action? The action could be apply any of these motors, apply any forces, or making these mates on and off. As you can see, it could be a change with a value, with a duration, and a profile. Let's have a review of the first task I have created. The first task named push SOLIDWORKS. It's getting triggered from a sensor. Now let's pause here and look at what is the sensor look like. All right. So in order to create a sensor, you are going to evaluate tab and click on the sensor. You have the option to have a mass property sensor, a simulation data sensor, dimension sensor, interference detection sensor, measurement, proximity, casting data, or motion data. In this case, as we would like to see, if this box is getting close to the sensor left, I would like to get an alert. Similarly, if the other box, hollow box, is coming approximate to the right sensor, I would like to get an alert. So by doing the create sensor, as I have created, you can see approximately sensor using base one of this sensor, this component, and considering these two blue boxes. The sensor will get the approximately and recording their distance, and when it's coming to a 12 millimeter distance between these two objects, it will give me an alert. Same, I have the second sensor, which is simply the hollow box as in highlighted blue, and face of that component, same distance, and I'm getting the alert. So I've defined my sensor separately, and then I've created a task, say push solid box. It's getting triggered by a sensor 1 as I have selected. It gives me an alert with the delay time of 0.1 second. It's going to trigger this action. This action is simply actuator 1, as you can see here, is going to change its position and move 75 millimeter during 1 second. This change or displacement could be selected to be linear, constant acceleration, harmonic, cyclodical, and cubic. So either of them is simply you can select. So if we have a look, we said if this object is coming close by the first sensor, activate the actuator to push by 75 millimeter during 1 second. You can see it's a big list of the tasks I have created. After that, it is reacting the actuator. Then the second actuator is pushing the solid box to the bay, retract it, and then push the hollow box, and. So I would like to have a program or schedule that it is an event getting triggered and action can be done here. Okay, let's have a review. Play the animation. You can see the boxes are dropping. The proximity sensor detected. The actuator come through by 75 millimeter. Same time, the other actuator is pushing the box into the bay while this one is retracting. Again, the other one, which is talking about the hollow box and needs to be go here, is retracting by 130 millimeter. While it's getting retracted, the other actuator is pushing the hollow box into the bay, and it's keep continuing of doing the same job. Each task has been triggered, an action has been done, finish, the second job is simply coming through. So it's your job to say what is happening, when is happening, and how should be performed. The first thing could be a sensor to trigger the event, or the previous task if it's been finished. So task end, if the push solid is being end, the actuator is moving 50 millimeter. If the sensor is getting alert, the actuator is going to forward 130 millimeter. So such as this one, you can simply program your feeder sorter as you can see, or your system as you might like to perform by saying a task, what is trigger the task, how much delay you would like to have on your task, and what sort of action is happening. Okay, guys, so this is an event base, and the difference is we are doing the task and triggers an action in compared to time acting or disactive some let's say forces or motors or etc. Alrighty, guys, so that is concluding my presentation. Well, what I would like to do at this stage is to simply have a quick review about how you can contact us. So simply Motion is an add-in product to your SolidWorks CAD. So you need some certain licenses to have this product active. There is a 2-day training for motion simulation, and we're going through a lot of case studies and more options you have. We're going to have more, let's say, zoom into our, let's say, motion analysis tool. If you have any inquiry about the pricing or you need any further information, please contact your account manager at InterCAD or email johnbelsham@intercad.com.au. I would like to thank everybody for attending and wish you all the best.
Stop.
Perfect.
Coming on.